So, lots of deep material we're looking at here. We finished off saying yesterday, last class, that we can, from the periodic table, tell you how many protons, how many electrons, how many neutrons, atomic mass, symbol, and name. And there's even more information than that. Remember that the electrons are arranged in, what was the magic word began with the letter S? I heard it here. Shells. So that word's going to go, wow, this is going to irritate me like crazy. I'm back. Shells. What are they arranged in shells around? What's at the center of the atom? Begins with the letter N. Around the nucleus. And here is the big theme for the next few days, David. How they are arranged in shells determines how they react with other atoms. Elements are related to each other in the same family or the same or vertical column, I should say vertical column, because that's what we mean by families, think vertical. Because they have similar properties, I'm going to be even more specific. They have similar properties because their electrons are arranged in a similar way. Specifically, Jimmy, their outer shell. You got the notes? You got the notes? You writing this down? Yes? Okay. Let's be even more specific. All alkali metals, that's family number 1. That's the first column. They have one electron in their outer shell. That's why they're so reactive, because they want to get rid of that one outer shell electron, and it's really easy to get rid of one outer shell electron. They're going to react with a lot of stuff. You saw the video of them blowing up in water. They react with lots of things. All noble gases, that's the far right of the periodic table, that's family number 18, they have full outer shells. And the fact that they have full outer shells, Gabe, that's why they don't react with anything. We used to say they can't react with anything. We now know we can force a couple of them to react, but basically I'm going to say they don't react with stuff. That's why they're called noble. You had this idea of a noble king sitting there prim and proper, or a noble queen sitting there prim and proper, not reacting to anything, always keeping a straight emotion. They didn't interact with the common atoms, the common folk. That's why they named them noble. Here is a word that you're absolutely going to be asked on your next test. The electrons in the outer shell determine how the element will react, and they are called valence. I'll capitalize it. You don't have to, just so it stands out. Valence electrons. V-A-L-E-N-C-E. Valence electrons are very, 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 very important. Almost all of the action that occurs when atoms combine with other atoms to form compounds, it's because of what's going on the outer shell, the valence electrons. The inner shell electrons don't have much to do with it. Niels Bohr was the first scientist to show that electrons exist in shells. He developed models to show how the electrons were organized. I wrote here, look at page 66. If you have your textbook, look at page 66. The picture you're looking at is this one, so I put it on the screen, but I didn't include it in your notes. So if you have a textbook, you can look there. Otherwise, I'll also zoom in here a little bit. I think if I go to 200, we can still get it on one screen. Pretty close. Yeah. Okay. What pattern do you see? So these are models of what atoms look like based on their electron shells. So in the first row, we have helium and hydrogen and helium. First row, one shell. First period, one shell. Second row, second period, how many shells, how many little circles do you see? 2. These are all atom electrons that will exist in the second shell. Keep going, third period, third row, how many shells? 3. But not only that, as you move to the right, you're adding one more electron in the outer shell. So lithium has 1 electron in its outer shell. Beryllium has how many electrons in its outer shell? Can you see? 2? No, outer shell. 2. How many electrons does boron have? 3. How many electrons in its outer shell does oxygen have?
7.
Count carefully. 6. 6. Okay? And the reason the noble gases are so stable, are so non-reactive, they have complete or full outer shells. Now you're going to learn in a little bit that the first period, the first shell, the first row, can only hold 2 electrons. How many electrons? Come in! Let me just pause the video here for a second. The first shell can only hold 2 electrons. By the way, how many elements are there in the first row? That tells you how many electrons that shell holds. How many elements are there? Leave your hat alone, David. Call the attention span. Stay up here. How many electrons are there in the second period, in the second row? How many elements are there? 8. That second row, that second shell, can hold 8 electrons. Okay. In fact, you're going to learn something called the 2-8-8-18 rule, because that's how your periodic table works. It's 2 in the first shell, 8 in the second shell, 8 in the third shell. And Mario, you don't have to memorize this. You can see it's all hidden in the periodic table if you're clever, if you count. And then 18, which is a bit much to count. Oh, wait a minute. They numbered the families across the top there. It's 18 along the top, so you can even get that. Other things. It turns out when electrons tend to form shells, they tend to pair off. We'll talk about that later on. So lots of patterns there. So, patterns in electron organization. As you move across to the right, the periodic table, as you move across the periodic table, the number of electrons increases by how many each time you move one? Yep. Okay. And now you're starting to see, David, why the periodic table has to have the shape that it does. As you move down the periodic table, the number of shells, electron shells, increases by 1. You get one whole shell each time. That's why potassium, find potassium on your periodic table. Element number what? Find it. Potassium on your periodic table. Element number what? 19. That's why it has to be at the beginning of the first row. We couldn't stick it on the end next to argon. That wouldn't make sense because it started a whole new shell. Okay. Now you can ask, Mr. Duke, how did we figure all this out? And the answer is some really complicated math equations. Bohr's model of an atom really is an answer to a very complicated math equation. It's the fact that energy is quantized, and if you've heard the term quantum physics, that's how they showed that this is true. So, if you ever want to distribute electrons, you are going to be asked to draw Bohr models of atoms. What I mean by that is you're going to do circles and more circles and more circles, and then dot in where the electrons go. Now, electrons aren't really dots. This is a model, but it'll work pretty good. So how do you do that? First thing you want to figure out is what row, and you can put in brackets period, because that's the fancy word for row, is the element in. How far down is it? This tells you how many shells have electrons in them. The inner shells will be full. The outer shells will have gaps or holes. They won't be full. They're missing some electrons. And the fact that they're missing electrons, that's what explains how atoms combine. We'll get into that in more detail. Count over from the left. Boom, 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 boom. This is the number of valence electrons. What does valence mean? I used that word on purpose. What did we say valence meant? I said it was really important. You better go look at your notes. Okay, so that's the number of outermost shell electrons. I wrote here, some students choose to remember the 2-8-8-18 rule. Can you see where it comes from? Look at your periodic table, Jimmy. It's 2 in the first, 8 in the second, 8 in the third, 18 in the fourth. We're not going to go past there. I could give you one 6 rows down to draw. It would just be so cumbersome. It would take up a whole page. Forget it. Then what do? You fill in the inner shells with pairs of electrons as shown below. Did I give you some dotted circles to draw in the notes? Let me just see on the back page. Yep, we're going to do carbon together. On the back page of your handout, so flip your notes over. I'm going to zoom in like crazy. Now, you can totally freehand these. My problem is when I draw a circle, it never looks like a circle. It looks like an amoeba. So, all right. Here's how you would do this. The first thing we want to do is we want to tell the person what atom we're drawing. We are drawing carbon. Don't write carbon. There's a symbol for carbon we're going to abbreviate. So underneath it, put a big little C right there. Carbon. That innermost circle is the nucleus. Inside the nucleus are protons and neutrons. How many protons does carbon have? How do you know? So here's what you're going to write in here. 6p pluses. How many neutrons does carbon have? You'll have to do some subtracting. Oh, is it also happens to be the same? Again, don't always assume that protons and neutrons are the same. It's mass minus atomic number. 12, take away 6. So we're going to go 6n0. Next question. What row is carbon in? Row means counting down. Second row. So the innermost shell is full of electrons. How many electrons can the innermost shell handle? So here's the rule. Electrons pair up once the shell is full. If you did this, don't write this down. Yeah, don't do that either. If you did this, don't write this down. I would take a half mark off. Instead, they pair up. So put 2 dots like that. Move down to the next row. How many electrons are there going to be in the valence shell, in the outermost shell? Count over from the left until you get to carbon. 4. So here's how it works. Look up. I'll wait till you look it up. Ready, Mansion? Don't write this down, just watch. This is why I said you want your periodic table out and in front of you a bunch of times. I told you to take it out. I know what I'm talking about here, Mansion. Okay? You want your own in front of you so you can see all of this. Got me? Okay. Back to what I just said. Allie, how many electrons does carbon have if you count across in its valence shell? Allie, how many electrons does carbon have? You got your periodic table? Count across. How many electrons does it have? 4. So you ready? Look up, look up, look up, look up, look up. We go like this. 1, 2, 3, 4. Now, if there... Wait, look up, look up. If there was more, now they would start to pair. If we were further down, if we weren't doing carbon, if we were doing, for example, phosphorus, we would go pair, pair, until we fill up that shell. So you start out doing the 4 points of a compass, up, down, left, right, and then you start to pair them up. That there, though, you said 4, right, Allie? Have I got 4 atoms in my, electrons in my valence shell? That is a Bohr model of what carbon looks like. Draw that. You okay with that? Next to there, let's do chlorine. Cl. What's the nucleus going to look like? How many protons? So I'm going to go 17p pluses. How many neutrons? Probably not 17. Sorry? I heard 19, I heard 15. Someone's right, someone's wrong. What's its mass?
36.
So 36 take away 17, 19. And again, if you're not comfortable doing two-digit math in your head, get a calculator. 19 neutrons. What row is it in? Third row. So 3 shells, and the last one is going to be not full. First shell, how many electrons in the first shell? So I go 1, 2. How many electrons in the second shell? Count carefully. It's 8. Count across. Second row, lithium, beryllium, boron is 8. Can I borrow your tape? Ready? Look up. 1, 2, 3, 4, 5, 6, 7, 8. Right?
No, but chlorine's right here.
Oh. No. We're doing the second shell right now. The second shell, not the outer shell. Second shell, totally full. How many electrons in the second shell? 8. We haven't got to the third shell yet. We got to do this right. So the second shell is going to have 1, 2, 3, 4, and then pair 5, pair 6, pair 7, pair 8. That's the second shell. Still not the valence shell. Boom, we move down to the next row. This is the valence shell. Mentioned how many electrons in the valence shell? How many electrons in the valence shell? Not 8. No. You guys are missing this. Ready? Now we're in this row. Count with me, mentioned. 1, 2, 3, 4, 5, 6. There's chlorine. How many? 7. Okay? You with me? No. We can't have kind of. Look up. So the innermost has 2. The next one has 8, and it's full because our element is in the third row. So it's going to have 3 shells. And the third shell is the one we have to count carefully. This is why I said, by the way, some students memorize the 2, 8, 8, 18 rule. You can just do the innermost shells if you happen to know those numbers. So how many did you say? So it's going to look like this. Ready? We go 1, 2, 3, 4. How many more? 3. 3 more. Folks, please, we've got to be careful. Don't say wrong answers to make jokes or anything like that. 3 more, and they're going to pair up. Pair. You can pair them up with whichever ones you want, but that's what it would look like. That is a Bohr model of chlorine. We're going to be practicing this an awful lot, but this is what's going on at the atomic level. Go back to where we were in the notes. I wrote here, finishing touches. We did this on the fly, so the atomic mass, we already said, is the average mass of the atom. And mass is equal to the number of protons plus neutrons. So that you can use that, since you know the number of protons, it's the atomic number, to figure out how many neutrons we subtract. Little nerd note. The reason the atomic mass is a decimal is because the number of neutrons can vary. That was what led us to the discovery of radioactivity, which you'll look at, I think, in Science 10. And so the mass is an average. Nerd note, Nick, typically if the mass is really far from being a whole number, like a 0.4 or a 0.6, that probably tells you that particular atom has a bunch of radioactive isotopes. If the mass is really close to being a nice whole number, not very radioactive. You don't need to know that. That's why I didn't include it in the notes. So, what are the steps? If we want to figure out the nucleus, what did we do? The first thing we did is we rounded off the atomic mass to the nearest whole number. My abbreviation for the word number is a number sign. Hopefully I've told you I tend to abbreviate. Then what? You subtract the atomic number from the mass. And the answer is the number of neutrons. Okay. How many neutrons are there in an atom of boron? How did you figure that out? What? Take away what? So 11 take away 5. Atomic mass 11, rounded off. Atomic number 5, 6 neutrons. How many in argon? What's the mass? In other words, what do you do? What take away what? 40 minus 18. Okay, 22 neutrons. Early on, you'll notice often atoms have the same number of protons and neutrons, but that pretty quickly stops happening. And again, the further down you go, Allie, the more weird stuff occurs. Okay. I wrote here, put the number of neutrons and protons in the nucleus of the Bohr diagram. Did we do that already? But that's whenever I ask you to draw a Bohr diagram, make sure you remember to do that. So you do the nucleus, and then you work your way outwards doing the electron shells. Put your pencils down. So your homework, and you can finish this in class pretty easy here, I think. It's called section 2.3 homework. So complete the following words: number or mass, atom or ion. Here is a chart where you can try and figure out. Now, the tricky part that we haven't, you know what, I'm going to say for now, this page don't do yet. I'm going to assign this page on Monday when we come back. Okay? What you can do is that one there. People at home are going, what's going on? So you could do number 1, 2. The only problem is they didn't leave you anywhere near enough room to draw the Bohr diagrams. I would say do them on a separate piece of paper and just staple them on when you turn this in. You're not going to turn this in yet on Monday. I'm giving you a head start, because I did promise you no homework for the long weekend, but I don't want you to sit here and waste 15 minutes. So you're capable of doing that one. You're capable of doing number 3. You're capable of answering number 4. I haven't yet talked about the ion charges here. You can do all of this page, so you can do 1, 2, 3, 4, and 5. And I'll say we'll just pause there for now. You can work on that. If you don't get all of it done, this isn't due Monday when you come back from your long weekend. I'm going to be continuing with this, talking about ion charges and noble gases and things like that. And I'll have more practice for you as well. Okay?